Hi, I'm Riccardo Vinciroli, and today I'm going to talk about using QM networks to model and analyze software performance antipatterns in cyber-physical systems. This has been investigated in our paper titled QM-based modeling and analysis of software performance antipatterns for cyber-physical systems, a joint work with Connie Smith and Katia Trubiani, accepted at the International Conference on Performance Engineering 2021. In the software development process, performance evaluation is a crucial activity. The early identification of performance flaws is essential since the cost of fixing errors grows exponentially with the project life. However, the identification of these problems is a non-trivial task, especially when considering specific domains such as cyber-physical systems whose heterogeneous software and network components make traditional techniques fail. In our paper, we identify performance issues in cyber-physical systems using the available software performance antipatterns. There are two main advantages associated with using software performance antipatterns. First, they include the description of problems leading to performance issues. And second, they provide best practices aimed to get performance improvements. Last year, 3 new antipatterns that apply to cyber-physical systems have been presented. They are we there yet? Is everything okay? And where was I? The are we there yet antipattern applies to requests that use computing resources to check the occurrence of some events. You can imagine kids on the road trip that keep on asking to their parents if they have reached their destination. The problem associated with this antipattern is the overhead generated by a too frequent check-in with respect to the time it takes for an event to occur. It can be solved by adjusting the check-in frequency. Is everything okay? Is observed when requests want to verify the status of computing resources. In this case, think about a waitress that checks if customers are happy with their food too often. To solve this antipattern, the platform status checking should be changed. For example, the status check may be triggered by some predefined events, states, or time. The where was I antipattern represent processes that forget their state and need to recalculate it, generating a lot of overhead. The where was I antipattern can be solved in different ways. For example, saving the state, checking if previous results apply, invoking context-dependent actions, or using a custom design solution. Our goal in this paper is to model these 3 antipatterns using QM network and analyze their effects on a real case study, which is QM networks since they have been demonstrated to be effective in real-world scenarios, and for their clear and simple representation of a system that is useful when describing and modeling performance antipatterns. First, we define our baseline as a simple and abstract closed system made of a delay station and 2 resources, for example, a device and a server. In the table, you can see the input parameters that we used for our baseline and the performance indices obtained by solving the model with the mean value analysis. Results from simulations are shown in the figure as a function of the service demand of the server. The usage of the 2 resources, the red and green lines, is plotted on the right y-axis. Initially, the device is the bottleneck of the system, but when the service demand of the server increases, the bottleneck switches. The system response time, the blue line, is plotted on the left y-axis, and it starts increasing when the server becomes the bottleneck of the system. The 99% confidence interval of all these curves is shown by the shaded area. Then, we decorated the baseline to model the 3 performance antipatterns previously described. For simplicity in these abstract models, we assume that the antipatterns are affecting only the device station, but in a real case, they can affect any resource of the system. Are we there yet? Is modeled by adding a new workload, namely check, whose request loop on the delay station and the resource affected by the antipattern. On the right, the effect of this antipattern is shown. Checking the occurrence of an event too often leads to performance overhead, perceived as an increase in the utilization of a resource that prevents other resources from accomplishing their work. Most likely, the overhead will switch the system bottleneck and slow down the overall computation. Is everything okay? Is modeled similarly to the are we there yet antipattern. However, in this case, the time between 2 status checks, that is the think time of the check workload, follows a deterministic distribution since we assume this check is coded in the application. We also assume that the average time spent by the check workload at the device is much smaller than the time spent by other requests at the same station. Results show that the effect on performance of this antipattern is similar to the one of Are We There Yet? However, due to the short processing time required to retrieve the status of device components, in this case, the performance overhead is generated by a high frequency of checking a resource, not from the checking activity itself as observed for the Are We There Yet antipattern. Where was I? Is modeled by increasing the time spent by a request at the device of delta time units. As expected, the greater delta, the longer the system response time. When recalculating a state becomes more expensive than the actual computation of that state, the response time can dramatically increase and the system bottleneck switches. The effect of these antipatterns is evaluated by applying them to a sensor net, a real example of a cyber-physical system. This case study analyzes an existing data acquisition system and machine control actions triggered by sensor values. It was designed to evaluate the resiliency of cyber-physical systems that must be guaranteed without sacrificing the performance. This case study shows how both security and performance can be analyzed before implementation, and how the performance models can quantify the effect of performance antipatterns that may be present during the design phase. The data acquisition system is modeled by using a multi-formalist model made of queuing networks and Petri nets. Let's look into it. First, note that the Petri net in this model is used only to represent the data generation and acquisition and does not affect the way we model the three performance antipatterns. There are 60 data requests in the sensor net, and each one spends 7.5 milliseconds in the generate data delay station before generating the data to the send data immediate transition. Such a data is placed into the data place and will be acquired and analyzed by the controller unless a new data is generated before the current one is acquired. In that case, the old data is dropped and replaced by a new one. In other words, we assume that only the most recent data can be pulled and analyzed by the controller. That acquisition and analysis are modeled by the polling and analysis workloads. These two workloads are mutually exclusive and they cannot coexist in the system. The polling workload is also used to model and investigate the effects of the Are We There Yet antipattern, whereas the analysis workload is used for studying the Where Was I antipattern. Every 0.1 milliseconds, a polling request spends another 0.1 milliseconds to be processed by the controller. Then it checks if new data is available. If no data is found, the request goes back to the delay station, where it spends again 0.1 milliseconds before being processed by the controller and checking for new data. Otherwise, if a data is found, the polling request is switched to an analysis request. Such a request is processed by the controller in 3.41 milliseconds before taking another 1.8 milliseconds to write some data in the database. Then the analysis request is switched back to the polling one and sent to the delay station. Status and exception workloads model requests that checks the status of some sensors and raise exception if something is not working correctly. The status workload is used to analyze the impact of these everything okay antipattern on the system performance. After waiting for 0.1 milliseconds in the delay station, a status request takes another 0.1 milliseconds to be processed by the controller and is sent to the sensors. Here it spends 1 millisecond to check that everything is okay. With probability 1 minus p, no problem is detected and the status request goes back to the delay station. Instead, with probability p, an exception is raised. In this case, the status request is switched to an exception one. This will be handled by the controller in 5 milliseconds before being switched back to a status request and sent to the delay station. The actor's workload models additional workloads that perform some actions on the data. There are 5 actors in the system. Each one thinks 30 milliseconds in the delay station, is processed in 2.16 milliseconds by the controller, and reads data from the database in 1.2 milliseconds. For each workload, we compute the utilization of the controller and the system response time to validate our queuing Petri net model against execution graph that have been used in the past to model the same sensor net. We use speed to analyze the execution graph and GMT to simulate queuing Petri net. Note that this is a comparison between the two formalists, not between the two tools. The error observed on the two performance indices is very small independently of the considered workload. It is always smaller than 6%. This means that the model that we propose is currently representing the cyber-physical system under analysis and can be used to evaluate the impact of performance antipatterns. We can now analyze how the performance of the sensor net degrades when it is affected by the three antipatterns. Are we there yet? Is observed by a change in the polling frequency, or the think time of the polling request. When the think time is too small and the polling frequency is too high, the controller looks for new data too often and its utilization increases tremendously. Similarly, also the system response time of other workloads that must be processed by the controller, in this case the actor workload, increases with the polling frequency. As previously said, the impact of is everything okay on the system is similar to the one observed for Are we there yet? However, processing a status request generally takes less time than polling data, and we can see that the system performance does not change much when only one status request is into the system, independently of the frequency with which the controller checks the status of sensors. The effect of the is everything okay antipattern is better visible when the number of status requests is larger than 1. For example, it is 5. And it is evident when there are 10 or 20 status requests. In this case, the utilization of the controller, as well as the system response time of the analysis and actor workloads, are 2 times larger when the sensor status is checked too often, that is, when the think time of the status request is too small. The where was I antipattern is analyzed by varying the service demand of analysis request at the controller. In the figure on the left, we can see that this antipattern slightly increases the controller utilization and doesn't affect the system response time of other workloads, for example, status or actors. However, on the right, we plot the data drop every second by the system, that is, the data that has been replaced by more up-to-date information. The longer the controller takes to recompute the state of the analysis, the higher is the number of data drop every second. Indeed, polling and analysis requests cannot coexist in the sensor net, meaning that when the controller is acquiring data, it cannot analyze them and vice versa. Dropping data is unacceptable in a data acquisition system. For example, if the data of an aircraft traffic system are dropped without being analyzed, the consequences could be tragic. So the input of the where was I antipattern on the sensor net is shown by the data drop rate. We are currently working on a journal extension of this paper where we also investigate how to avoid drop of data at the model level. For this purpose, we built a no-drop model and preliminary results seem promising. In this paper, we use queuing networks to model software performance antipatterns of cyber-physical system and showed that this formalism allows recognizing and analyzing performance problems. We injected performance antipatterns into SensorNet and used queuing network models to analyze the whole system. We found that performance antipatterns may have a huge negative impact on the performance of a cyber-physical system, and that is crucial to early identify bad practices. In the future, we want to develop a framework that keeps track of required information and exploits the provided queuing network models to automate the detection and solution of performance antipatterns in cyber-physical systems. We also want to determine which antipatterns contribute more to the violation of requirements to prioritize their solution. And finally, we aim to consider other industrial cases to investigate the impact of performance antipatterns in different application domains. That is all. Thank you for watching this video and do not hesitate to ask us any questions. You can also use our tool and scripts for your own research. They have been evaluated by the Artifact Committee and awarded with functional and available badges.